There is a prequel to the Da Vinci Code. It's called Angels and Demons. And in it, terrorists steal 1/8 of a gram of antimatter from CERN to try to blow up the Vatican. Because the thing is, when antimatter and matter meet, they annihilate, turning nearly 100% of their combined mass into pure energy. This is via E equals mc squared. It is the most violent process physics allows.
Let's go! Oh my god.
Now, that was just a novel, but CERN actually is making antimatter. And we got to visit it. This is CERN's Antimatter Factory. There's antiprotons going beneath our feet.
They are under our feet at this time.
Here, protons are accelerated up to 99.93% the speed of light and smashed into an iridium target to produce 20 million antiprotons every minute. This is so much bigger than I was thinking. This is crazy. Antimatter is the most expensive substance in the universe. $1 billion per gram.
No way, go up. We are missing zeros here.
Okay. And CERN makes it to do something that seems impossible. So you're making anti-atoms?
Yes.
CERN made the first anti-hydrogen atoms back in 1995. But they quickly ran into a problem. Because those anti-atoms only survived for 40 billionths of a second before annihilating, which is way too short to do anything useful with it. If only they could figure out how to store antimatter, then they could study it and try to find ways in which it might differ from normal matter. They knew that any unexpected difference could reveal entirely new physics. So how do you store antimatter in a world full of matter? Well, that's one of the problems CERN has been obsessing over for the last 30 plus years. It has allowed them to do some of the most precise tests of antimatter to date, and they even managed to trap antimatter in a box, load it onto a truck, and ship it. And they are doing all of this to try and solve one of the biggest unsolved mysteries in all of physics. To understand it, we must go back to a discovery made around 100 years ago.
Previously on Veritasium, we learned how a strange physicist, Paul Dirac, came up with an equation to unite special relativity with quantum mechanics. It worked surprisingly well, but Dirac was stumped by his own equation, because the solution for an electron at rest was kind of strange. There were two possible energies, E equals mc squared and E equals minus mc squared. But how could an electron have negative energy? Well, instead of throwing away his negative energy solution, Dirac ended up proposing something radical. This negative energy solution corresponded to an entirely new particle, unknown to physics at the time. It would have the same mass as an electron, but carry opposite charge. It would be an anti-electron, or positron.
Miraculously, a year later, the first positron was observed by accident in nature. Over the following decades, physicists built on Dirac's equation to form an entirely new framework of quantum mechanics. Quantum field theory. This didn't just explain why there are antiparticles, but it also answered a more fundamental question, which is, why is every electron in the universe exactly the same? The answer began to take shape when people figured out that fundamental particles aren't just particles or waves, but rather excitations of a quantum field. So you'd have an electron field that permeates all of space, and this field can get excited, but only in identical discrete units, each with the same mass, spin, and charge. And that's why every electron is the same. They're all excitations of the same field. Now, you could have several excitations, that would be several electrons, and they can move around too. The only requirement is that they can never overlap exactly. Of course, there is nothing special about this kind of excitation. You could just as well have a mirror opposite. In fact, the equations that describe this field require such excitations to exist. They have the same mass and spin, but with opposite charge. This is the idea of an anti-electron, or positron. It's exactly what that minus sign in Dirac's equation was revealing. And just like an electron, positrons can move around too. Only positrons can overlap with electrons. But watch what happens when they do. Now, I'm simplifying a little here, but because they're each other's mirror images, the opposite charges cancel each other out. The excitations disappear, and the field returns back to its ground state. But that would predict that the particles just disappear. So how is that possible? Where did the mass go? Well, the only way this could work is if that mass got converted into something else. Energy, according to E equals mc squared. The energy got transferred into a different quantum field, the photon field. And that is what we mean by annihilation. Now, people realized that most fundamental particles could be described using the same approach, where each could be seen as an excitation of their very own quantum field. Now, this meant two things. The first is that most particles must have an antiparticle twin, because they're just mirror excitations in the same field. There are some exceptions though, like the photon and Higgs boson, which are their own antiparticle. And the second and more important implication is that each antiparticle must be exactly equal to a normal particle, just with the opposite charge. But then, around the mid-1960s, people realized that there was a big issue with this explanation. And it all stemmed from how it fit in with the newly accepted Big Bang theory.
In the very first moments after the Big Bang, the universe was extremely hot and dense, and photons had so much energy that the reverse process of annihilation happened. So two photons could come together and spontaneously convert their energy into the mass and kinetic energy of a particle-antiparticle pair. And so the universe was filled with these pairs continuously popping into and out of existence. But as the universe continued to expand, it cooled, and those photons lost energy. Until around 3 seconds after the Big Bang, they had lost so much energy that pair production stopped.
And this is what troubled physicists in the 1960s, because they believed that in those initial stages, an equal amount of matter and antimatter should have been created. But if an equal amount of matter and antimatter were created, then every particle should have found its antiparticle twin and annihilated. Meaning there should be no stuff around us, no matter and no antimatter, just photons, only radiation. So this became known as the Big Bang radiation catastrophe. Because clearly, when we look around us, we see a lot more than just energy. The universe is filled with matter. But how can that be? Why is there now more matter than antimatter in the universe? Where did that asymmetry come from? Well, that is one of the biggest unsolved mysteries in all of physics. Initially, some people tried to brush this away, and they argued that perhaps there is no asymmetry at all.
Maybe we happen to be in a pocket that, because of blind random chance, some reasonable statistical fluctuations, we're mostly surrounded by matter, and there'd be some region that would again be like a Marvel movie, like some mirror universe that would be most slightly, imbalanced in the other direction.
Paul Dirac seemed to have favored this approach. He argued that there might be entire anti-stars, and he ended his 1933 Nobel lecture by saying, "There may be half the stars of each kind. The two kinds of stars would both show exactly the same spectra, and there would be no way of distinguishing them by present astronomical methods." Physicist Edward Harrison took this one step further, saying there should even be entire anti-galaxies.
And then people realize, well, if that's the case, there'd be regions where these boundaries where the two regions would meet, and that should be lighting up the sky. Should be tons of matter-antimatter annihilations. Should be tons of very high energy light.
So people surveyed the sky looking for these hotspots, but they didn't find any. And so this possibility was ruled out. There really is more matter than antimatter in our universe. There really is an asymmetry. So the next obvious question is, well, how large is that asymmetry? If we go back to around 10 seconds after the Big Bang, we can figure it out.
By this time, pair production had long stopped, a full 7 seconds ago. And by now, just about every antiparticle had annihilated with its particle counterpart and turned into photons. Now, the universe was filled with just some leftover particles, like electrons and protons whizzing around at incredible speeds, and those remnant photons. But because these electrons and protons were traveling so fast, they couldn't come together to form atoms. So you had this plasma of charged particles. And that meant that when photons were going around, they scattered off those charged particles. So they couldn't travel very far without interacting with matter. That all changed around 380,000 years after the Big Bang. By now, the electrons and protons had slowed down enough to form neutral atoms, and photons could only be absorbed by electrons in atoms if they had exactly the right energy to move the electron up an energy level. In practice, this meant that photons could now basically travel through space unimpeded. Those atoms then went on to form all the stars and galaxies, and those photons stuck around too. They've gone on to make up the low-level radiation that permeates the entire observable universe, the cosmic microwave background, or CMB. And when we estimate the total number of photons in that CMB, we find that there are about 10 to the 89. And because almost all of those photons were originally created during those very first seconds after the Big Bang, that original annihilation, we can infer that there must originally have been around 10 to the 89 particles and antiparticles. Now, we can also estimate how many ordinary matter particles, like protons and neutrons, there are in the observable universe today, the ones that survived that annihilation. And what we find is that there are about 10 to the 80. So that means that for every billion antimatter particles and billion matter particles there were in the early universe, when they annihilated, they did so almost perfectly. But there was one out of a billion matter particles that somehow survived. And everything we see around us today is a descendant of those lucky 1 in a billion particles. Every person, animal, jungle, and ocean, every asteroid colliding or galaxy spiraling, every single dot of light in the night sky is made up of one of those lucky 1 in a billion particles.
And that brings us to the craziest part, because it tells us that there must be a difference between matter and antimatter, and how they evolve according to the laws of physics. But it's not just any difference. No, it would make sense if they behaved completely different. I mean, you would just have different laws of physics governing each type of particle. Or it would make sense if they were governed by the exact same laws. But in that case, there would be no difference. It would be completely symmetric. What's really weird here is that the laws are almost exactly the same, but with a tiny difference. And that doesn't make any sense.
For the past 70 years, physicists have tried to explain where this asymmetry comes from. But so far, all attempts have failed. And part of the reason this has been so difficult is because our laws of physics are full of symmetry.
In the mid-1950s, there were 3 symmetries all particles were believed to obey: charge, parity, and time reversal symmetry. Charge symmetry is super simple. It just means that if you swap all positive charges with negative ones, and vice versa, then the interactions don't change. In other words, there is nothing special about a positive or negative charge, just that one is exactly equal and opposite to the other. To understand parity symmetry, consider this mirror, which creates a sort of parallel universe, where everything is the same but reflected. So my left hand becomes my right hand and vice versa. Now take this molecule here, which is L-alanine, an important amino acid we need to make proteins. Now that L is in its name because the amine group, this NH2 part over here, is on the left. But in the mirror you see its sister molecule, D-alanine, that NH2 part is now on the right. And if you try to make alanine in a lab, you'll find that you'll get 50% L-alanine and 50% D-alanine. In other words, there is no experiment you could do that determines whether you're in our universe or in the mirror universe. And the same is true for many left and right-handed molecules. If you just try to make them normally in a lab, you'll get 50% of each. So our universe doesn't favor left or right-handedness. Lastly, time reversal symmetry means that the laws of physics work the same whether time is running forwards or backwards. Now, out of all of these, time reversal symmetry might feel strange, because there are many things that clearly don't work backwards in time. You can't uncook an egg, unshatter a wine glass, or turn a plant back into a seed. But all of these follow from the second law of thermodynamics, which describes how many interacting particles evolve from less likely states, typically more ordered, to more likely states, typically a mess. But this is a statistical law. It's not a fundamental law of physics. If you zoom in to the level of individual particles, then every interaction is perfectly reversible. You can tell whether these collisions happen forwards or backwards in time.
Now, the combination of all of these symmetries combined is called CPT symmetry. And CPT symmetry, it turns out, is kind of a big deal.
What happens if CPT gets broken?
Well, literally, cats and dogs start living together. Time flows backwards. All kinds of things start breaking in our description of nature. Now, one of the reasons why CPT and the standard model go so well together is because it really is built into the very structure of special relativity.
Special relativity is built on one core principle, which is that the laws of physics are the same for all inertial observers, and this includes any measurement they make of the speed of light. In the 1950s, Julian Schwinger, Gerard Luders, and Wolfgang Pauli proved that if our universe obeys this principle, which we strongly believe it does, then it must be CPT symmetric. But the reverse is also true. If you break CPT symmetry, then this core principle also breaks. And that's where things get tricky. Because after Dirac united special relativity with quantum mechanics, all following quantum theories also incorporated special relativity. And so our best theories of reality, quantum field theory and the standard model, are built on that exact same principle. So now we have a paradox. Because on the one hand, we need asymmetry to explain why we're here. But on the other hand, if CPT symmetry breaks, it tears down our best theories with it. So physicists started off on a hunt for a special kind of asymmetry. An asymmetry that could explain that 1 in a billion discrepancy while also maintaining the larger CPT symmetry. The first clue that such asymmetries might exist came in the mid-1950s. Up until then, every interaction that had been studied conserved the individual symmetries of C, P, and T, and so conserved CPT as a whole.
But in 1956, theoretical physicists Soong-Dao Lee and Chen-Nin Yang realized that no one had checked whether parity is conserved in the weak nuclear force. So they set out to test whether the universe favored left or right-handedness. And to do it, they enlisted the help of one of Lee's colleagues, one of the world's best experimentalists, Chen-Shung Wu, also known as Madame Wu.
Once the idea of the experiment was pitched to her, then she just went all in. She canceled trips. She worked straight over holiday breaks. It was really a all hands on deck operation over a very frenzied few months.
When Pauli learned of the experiment, he said, "I do not believe that the Lord is a weak left-hander, and I am ready to bet a very high sum that the experiments will give symmetric results."
Now, all that was left to do was run the experiment. It worked something like this.
She started with cobalt-60, an isotope of cobalt where the nucleus has an intrinsic angular momentum, or spin. When she applied a strong magnetic field, she forced all the spins to point in the same direction. But cobalt-60 is also radioactive. So every once in a while, a neutron inside one of its nuclei decays into a proton, releasing an electron and antineutrino, and leaving a nickel-60 atom behind. Now, the electrons emitted could travel in two directions. They could either go in the same direction as the nuclear spin, or they could go in the opposite way. But if spin is clockwise in our universe, then it is also clockwise when reflected in the mirror, which means it points in the same direction in both universes. So the only way the experiment could be the same in our universe and the mirror universe is if the electrons were emitted in equal amounts in each direction. It should be 50% on each side. But what Wu actually found was that around 60% of the electrons moved in the opposite direction to the nuclear spin, which would mean that 60% moved in the same direction as the nuclear spin in the mirror universe.
But that meant that there is an experiment you could do to tell whether you're in our universe or the mirror universe. So it proved that parity is not conserved. This shocked the physics community.
Pauli, upon being informed of the results, exclaimed, "That's total nonsense."
Very smart people, Nobel laureate, said, "That can't be right. Do it again. I don't believe it." And in a sense, you can see where they're coming from. There had been no hint as yet that kind of the universe would care whether I'm looking at myself, in a mirror or not.
So others repeated the experiment, and by 1957, there was no further room for doubt. God really was a weak left-hander. That same year, Lee and Young won the Nobel Prize in Physics for the discovery of parity violation. But Wu's name was left off. Lee and Young acknowledged her during their speech and tried to get her nominated for a prize another year. But the Nobel Committee never honored her. In a way, she was robbed of the Nobel Prize. 1988 winner Jack Steinberger called this the biggest mistake in the Nobel Committee's history. But her work had done something important. It had cast doubt on the long-held belief that charge, parity, and time reversal were fundamental symmetries of our universe.
This made many physicists uncomfortable, so they came up with a workaround. Maybe it's okay if parity symmetry was broken, because that's not a fundamental symmetry of nature, it's just part of a larger symmetry, charge parity. The idea was that if you reflected everything in a mirror and swapped all the particles for their antiparticles, then the symmetry would be restored and all would be good again.
But then, 7 years later, two physicists found that some particles also violated the combined charge parity symmetry.
Now physicists were getting really nervous. Two symmetries that they believed were fundamental parts of our universe were broken. So the next big question on everyone's mind was, is CPT symmetry also going to fail and take down the standard model with it? Then, in 1973, something seemingly miraculous happened. Makoto Kobayashi and Toshihide Masukawa found a way to explain all the observed P and CP violation while maintaining CPT symmetry. And it all fit directly within the standard model. The only issue is that when it comes to the matter-antimatter asymmetry, it can only account for an asymmetry of 10 to the minus 18. Which is a billion times less than we need to explain the observed matter-antimatter asymmetry.
So the ingredients are there, which is cool, because we didn't think even the ingredients were there. But they're not there in a large enough strength. You don't have a strong enough rate of CP violation if you just stick with strictly the standard model.
And so are people now getting nervous about CPT?
Not nervous, I'd say excited.
And that's because this means there is likely new physics beyond the standard model. But to find out what that might be, we must study antimatter up close, to see if there are any ways in which it might be different from normal matter, ways that could explain that asymmetry. So you know where we're going.
Oh, look, there it is. CERN, baby. Woo!
CERN is best known for the Large Hadron Collider, a 27-kilometer underground ring where protons are accelerated up to 99.999999% the speed of light. Beams traveling in opposite directions are smashed together, releasing huge amounts of energy. It's the closest we get to the high energy conditions of the early universe. But at the southern edge of the LHC, there is a smaller proton accelerator called the proton synchrotron. Protons in this ring are only accelerated to 99.93% the speed of light. And some of that proton beam is fed out of the ring and ends up here.
This is CERN's Antimatter Factory. And in here, you make antiprotons.
Yes.
How many?
Usually it's around 40 million every couple of minutes. We are now going to enter the facility by actually a technical building, which is not very interesting to watch.
I find this all interesting to watch.
To make sure we're safe, we always had to carry around these devices.
So you've got two, what are they called?
Dosimeters.
Dosimeters.
Yes.
Yeah, just to be safe.
These are standard devices to measure the amount of dose of radiation that you get.
Yeah.
This is a supervised radiation environment, which means it's an environment in which we keep an eye onto the amount of radiation we get as radiation workers.
Where are we going now?
So now we are going to enter into the main building.
There's antimatter behind this.
Yeah.
Behind this door.
Yes, under our feet.
Oh wow.
Yeah, we see, you see. Please,
wow.
guys,
This
and
is
welcome.
huge. What?
This is a huge place.
This is so much bigger than I was thinking. This is crazy. Well, I feel like I'm a kid in a candy store looking at this.
This place is pretty fun, huh? The first time you see it.
Yeah, it's so impressive.
Here you see pretty much the scheme of how this facility is working. You get protons coming from one of the CERN accelerators, the PS, which smash onto a target.
The protons are accelerated up to around 99.93% the speed of light and have energies up to 26 giga-electronvolts. They're aimed at a remarkably small target, an iridium rod, 3 millimeters in diameter and 55 millimeters across, which itself is embedded in a graphite and then in a titanium alloy structure. Iridium was chosen because it's the second densest element on Earth. And that means that there are a lot of nuclei packed in a small space, which increases the odds that the protons will hit something. But when one of these protons hits an iridium nucleus, it doesn't bounce off like you'd expect in most collisions. It is going so fast and has so much energy that it penetrates the nucleus, where it collides directly with one of the neutrons or protons. And to understand what happens next, we need to look at what's going on inside the proton. Because a proton is not a fundamental particle. Instead, it is made up of 3 fundamental particles known as quarks, specifically 2 up and 1 down quark. Those quarks whiz around close to the speed of light. So to keep all those quarks contained, traveling at such incredible speeds and in such a small space requires a very strong force, which is why it's called the strong force. And it's mediated by particles known as gluons. You can think of this force as acting like a rubber band.
But you can bring this past its breaking point. If you keep putting in energy, then you can put in so much energy that another quark-antiquark pair will be created. This bond breaking into pair creation can happen several times in a row and results in this sort of shower of quark-antiquark pairs.
And a similar thing happens when a proton collides with a neutron or proton inside an iridium nucleus. Now, most of those pairs stay just like that, pairs, and they travel off. But occasionally, you will get 2 anti-up and 1 anti-down quark to come close enough, and they form a new particle made of 3 antiquarks. They form an anti-proton, and their counterparts will go on to form a proton.
Now, all of this entire process, from initial collision to the shower of particles and the formation of the antiproton, happened in the span of 10 to the minus 23 seconds. That is 100 billionth trillionth of a second. It is absolutely insane. And every time you hit the target, you get trillions of these collisions. And out the other side comes a chaotic spray of protons, antiprotons, and a bunch of other particles, all traveling at around 96% the speed of light. Magnets then filter out the antiprotons from the other particles and they're sent on to the next stage.
And then we collect these antiprotons, bring them into the ring, the antiproton decelerator ring, which is the one we are staring on top of, and then they circulate in the AD for a while they get cooled down. So the idea here is really that we get these antiprotons every 2 minutes, more or less. It's about 30 million of them.
How expensive is it, antimatter?
Look, guys, what is value? It's a bit difficult to evaluate it, right? For sure, it's probably the most expensive state of matter we can build on Earth today.
How about I name some numbers and you tell me if it's cheap or too expensive?
Shoot.
$1 billion per gram.
No way.
It's too cheap?
Orders of magnitude too cheap. But
Okay.
many orders of magnitude too cheap.
That's what I was thinking. $100 billion per gram.
No way, go up. I think probably you miss other 3 zeros.
3 zeros.
I think so, per gram, yes,
That's
at least.
crazy.
If you're wondering what you would do with all that money, you should check out today's video sponsor, SoFi. SoFi is an all-in-one finance app that lets you bank, borrow, and invest. And with their premium membership, SoFi Plus, you get benefits such as investment matches, unlimited access to financial planners, and a competitive APY on savings to earn interest on your money. All so you can let your money work for you. By adding up all of these benefits, you could unlock $1,000 or more in annual value with qualifying activities. Of course, it depends on how you use the app, so check if it's right for you. And you can get started by subscribing to SoFi Plus for just $10 per month. Right now, they're also running a promotion for US residents. So if you join SoFi Plus between now and April 15th, you'll automatically be entered into their giveaway for a chance to win $75,000, as well as other cash prizes and free memberships. So to check out SoFi Plus, head to sofi.com/Veritasium or click the link in the description. I'd like to thank SoFi for sponsoring this video, and now back to antimatter.
There's antiprotons going beneath our feet.
They are under our feet at this time, yes, indeed.
And that's not dangerous?
No, it's not dangerous. There's no risk whatsoever.
Strong electric fields in the decelerator slow down the antiprotons from 96% to 10% the speed of light. But that's still about 100 million kilometers per hour. To do experiments with them, they need to be slowed down more.
Initially, this was done in a kind of crazy way. The antiproton beam was fired at a thin plastic foil, which annihilated 99.9% of all the antiprotons. But around 0.1% of those antiprotons survived, and they came out slow enough to do experiments with them. Of course, this was very inefficient, and so in 2015 and 2016, a secondary ring called ELENA was installed. ELENA slows the antiprotons to 1.5% the speed of light. A nice, slow 16.2 million kilometers per hour.
This is running.
You are watching a live antiproton machine.
Are the antiprotons going around in these circles?
Exactly. The blue devices are magnets, dipole magnets, which by Lorentz force make the particles turn. Then you have the orange ones, which are quadruple magnets, which manage the focusing of this beam. They're like lenses for particles.
It's a pretty thin pipe almost that they go through.
Yeah, I mean, you don't need much there, right? Because as long as you don't bend the particles, they just want to go straight. You need to keep good vacuum in there, very good vacuum in fact. Otherwise they would annihilate.
And how often do you have annihilations in this loop?
In here?
Yeah, because you can't have perfect vacuum.
Well, no, you have a bit of losses, but you know, the entire process of catching, I mean, from the moment of catching to the moment of extraction to the experiments, I think these days we are about 86% efficiency. They have made it very efficient.
After the antiprotons have been slowed down in ELENA, they're sent onto 5 different experiments, each of which is designed to study different properties of antimatter, to try and find ways in which antimatter behaves differently from normal matter.
One of the first experiments that was done, which happened before the Antimatter Factory was built, was testing whether the mass of a proton and antiproton are the same. But to do that, it brings us back to our original problem. How do you store antimatter? The way they solved this problem is pretty clever. They started with a tube, which was pumped down to a vacuum. A superconducting magnet sits around this tube, and it creates a magnetic field that confines charged particles to the center. At the same time, electrodes generate electric fields that function as end caps, preventing the particles from escaping out the ends. The whole tube is then cooled down to around 4 Kelvin, or minus 269 degrees Celsius. This causes almost all the remaining particles to condense and freeze, resulting in a vacuum pressure comparable to outer space. So now they could fill this tube with something like antiprotons. And once inside, those antiprotons have nothing to annihilate with and nowhere to go. They are trapped. They had just built a real-life antimatter trap.
The technical term for this is a Penning trap, after Franz Penning, whose work inspired the first one.
Fittingly, the team that did this at CERN was called TRAP. With the antiprotons trapped, they measured the charge to mass ratio of the antiproton and compared it to that of the proton. And they found it was equal to 1 part in 10 billion. Now, the Penning traps made studying antimatter much easier, and so it became a key tool that the other experiments at the factory adopted. In 2017, the BASE experiment used it to measure the antiproton's magnetic moment, and they found that, within their level of accuracy, it was equal and opposite to that of the proton. So, thus far, everything was behaving just as predicted. But there is one force that they hadn't directly probed yet: gravity. Gravity, could that be part of the solution?
It very likely will be ultimately. Part of why is because gravity does not obey the rules of special relativity, which means it doesn't have to obey the CPT theorem like the CERN model does. And so in principle, that's an area within which one could more naturally expect larger values of violations of C and CP and so on, or even a CPT altogether.
In fact, back in the 1950s, a few physicists entertained the idea of anti-gravity, that antimatter would be gravitationally repulsive. So while matter falls down in the Earth's gravitational field, antimatter would rise up.
You had a basketball made of antimatter, that would be easy to test, but getting a basketball of antimatter without it blowing up on you is pretty hard. So it's not an easy thing to do gravity experiments on particles.
You can't just drop an antiproton and see if it falls, because antiprotons are negatively charged, and the electric force is much stronger than gravity. So even small stray electric fields would influence them way more than gravity would. So what you need is something neutral. What you need is an anti-atom.
So you're making anti-atoms.
Yes.
How do you make the anti-atom?
So what we do is we use antiprotons and positrons. Basically, we merge them, they become antihydrogen.
Now, there are several ways to make antihydrogen, and different experiments do it in different ways. But for G-Barr, it all starts here, in this bunker.
In this bunker, we have a small accelerator. So we make ourselves our own positrons, and then we capture them in a trap here.
They accelerate a beam of electrons up to 99.9% the speed of light, and then fire those at a tungsten target. Now, while tungsten itself is electrically neutral, at the high speed those electrons enter the tungsten, they get close enough to the nuclei that the electron cloud can no longer screen the intense positive charge within. Thus, these nuclei create strong electric fields, and those fields then yank the electrons around, causing them to rapidly decelerate, as if they've just slammed on the brakes. But the thing is, when these electrons break, they lose energy by emitting photons. The Germans have a great word for this. It's called Bremsstrahlung, or breaking radiation. This breaking radiation produces a wide range of photons, ranging from low-energy X-rays all the way up to nearly 9 mega-electron-volt gamma rays. Now, out of all of these photons, it's the gamma rays above roughly 1 mega-electron-volt that are important. Because when one of these gamma rays passes close to a tungsten nucleus, there's a chance that it transfers its momentum to that nucleus and converts all its energy into the mass and kinetic energy of an electron-positron pair.
But unfortunately, this isn't a clean process that just makes electron-positron pairs.
It produces positrons, but it also produces a lot of photons, gamma rays, neutrons, and these are deadly.
And that particle mass creates two problems. The first is that deadly radiation.
It's supposed to be one of the highest, strongest source of radiation at CERN.
This is one of the highest.
Yes. If you enter while it is working, you die in 10 seconds.
You die in 10 seconds?
You cannot escape.
It's terrifying.
You melt from inside.
You melt from inside. You're saying that way too casually.
And the second problem is that what comes out of the tungsten isn't a nice uniform beam of positrons. Instead, you get a shower of electrons, neutrons, positrons, and photons all mixed together, all traveling at different angles and different speeds. The first problem is solved by encasing the entire setup with massive 1.2 meter thick, 67% concrete and 33% iron blocks.
And this is enough to shield us?
Yes.
Because it's photons?
Yes. This is 1,400 tons.
Okay, I feel a bit better now. Is it running now?
No, but even if it runs, we can see just outside and it's okay.
Okay, so we're safe. You wear your
badge, dosimeter.
Okay, so you would know.
Yeah.
But I guess 10 seconds, not
Too late.
too late.
Solving the second problem is a little more involved, and it's honestly one of the coolest combinations of physics and engineering I've ever come across. So strap in.
When the positrons leave the tungsten target, some are traveling at a few percent the speed of light, while others are traveling at more than 90% the speed of light. Now, this massive spread makes it very hard to work with, so we need to slow them down to around 0.34% the speed of light, or around 3.7 million kilometers per hour.
The way they do this is kind of crazy, because they shoot the positrons, remember, those are antiparticles, at a mesh of ultra-fine 20 micrometer diameter tungsten wires, which of course are made of normal matter.
When a fast positron enters the tungsten wire, it immediately loses energy due to scattering off the tungsten atoms. And this happens so fast that within around 10 picoseconds, that is 10 trillionths of a second, the positron has slowed down to match the thermal energy of the tungsten. But now the positron is still trapped inside the wire. So from here on, through a random walk of collisions and scattering, it needs to find its way out. And if it bumps into an electron or gets stuck in a defect, it never makes it out.
So you might expect almost none of these positrons to make it out, and for almost all of them to find an electron and annihilate. And you'd be right. The efficiency of this process is terrible. For every 1,000 fast positrons entering the mesh, only about 1 comes out as a usable slow positron.
Another problem is that these positrons don't come out as a nice organized beam. Instead, they are emitted at all kinds of angles, so we need to find a way to focus them. This is done by letting the shower of particles go through a solenoid, which is a long coiled wire with a current running through. That current creates a magnetic field inside the coil that acts as a magnetic lens and focuses the positrons. This lets us capture many of the positrons emitted at wide angles that would otherwise be lost. But right now, we still have a mix of positrons, electrons, neutrons, and photons. So the next step is to separate these. To do this, we use another magnetic field. This curves the electrons one way into a beam dump. The photons and neutrons, because they have no electric charge, are unaffected, so they go straight through and are absorbed by shielding. And the positrons, because of their positive charge, curve the opposite way to electrons, and they go on to the next stage. Now we're left with a beam of just positrons. The only issue is that because of the terrible efficiency from slowing down those positrons, each single shot only generates around 1,000 usable slow positrons. But we need millions or even billions of slow positrons for the next stage. So the solution is to accumulate the positrons in a particle trap, where over several minutes it builds up a positron cloud of around 100 million or more positrons, which is enough for the next stage.
Oh, I said you merge positrons and antiprotons, but we do even more complicated. First, we make positronium. Positronium is
Positronium?
Yes.
Positronium is an electron and a positron orbiting each other like a binary star system. It's an exotic form of matter, and it only lasts about 1/10 to 142 nanoseconds before the two come together and annihilate. The way they make this is by using strong magnetic fields to compress the cloud of positrons and fire it at porous silicon dioxide films. When these positrons enter these films, they rip away electrons from their atoms, and some of those electrons then bind with positrons to form positronium. And then a part of that positronium diffuses out of the films into the vacuum of the next stage, the interaction chamber, where it's time for the final step.
So this is what we prepare this here.
That's the positronium.
Yes.
That's crazy.
We send antiprotons to the positronium where it makes antihydrogen.
Now, since positronium only survives for about 142 nanoseconds, this needs to be timed perfectly.
So if you want to see where we catch the antiprotons.
Yes, I would
there.
love to see where you catch the antiprotons. I was not expecting to get this close. It's right here?
Yes.
That's awesome. Yeah, so we get the antiprotons here.
Yes.
And then what happens?
So it goes there inside this box.
Yep.
Inside the box, it will meet the positronium.
Oh, there meets the positronium. Kind of scared, honestly. It sounds like there's music in here.
As the positronium enters the interaction chamber, the antiproton beam needs to be fired through at that exact moment. When done correctly, around 3 million antiprotons or so pass through the positronium. If all goes well, around 1 to a few of those antiprotons steal a positron to create an atom of antihydrogen.
Okay, so we've got positrons coming through here, all the way through here, and this is where you capture the positrons.
Yes, we accumulate them.
You accumulate them, and then you shoot them through there, and you make the positronium, and then you shoot that into that chamber, so it mixes with the antiprotons.
Yep.
So cool. It's so cool. Right in here is where they make anti-atoms, anti-hydrogen. They shoot the antiprotons through, and they capture they capture those anti-electrons to form anti-hydrogen, which then travels through here, and then, it will go all the way along there, and they do their experiments. It's absolutely insane. I feel like I should not be in here, but it's so cool.
Now, one question I had after learning all of this is why? I mean, why do this? Because the alpha G experiment can already make 100 antihydrogen atoms in 4 hours using a much simpler process. So why is the G-Barr team spending years to build a particle accelerator, a positronium converter, and a way to shoot the antiprotons through this positronium just to make fewer antihydrogen atoms in a slower and more difficult way? Especially when you consider that in 2023, alpha G did its own test to see whether antihydrogen falls up or down. Well, to understand why, we need to understand exactly what it is that alpha G did.
Their setup works something like this. Positrons are created by a radioactive source, accumulated, and are then injected up and trapped. Antiprotons then come in from Elena, are accumulated in a trap, and then also injected in a trap that sits just below the positrons. Next, the two antiparticle clouds are gently merged. This causes some of the antiprotons to capture a positron and form antihydrogen. Now, antihydrogen is neutral, which means that the penning trap can no longer hold it. So if nothing else was done, the antihydrogen atoms would form, drift off, and within microseconds annihilate at one of the walls. It would all be for nothing.
And this is exactly what happened with the earliest antihydrogen experiments. They couldn't hold on to it. Fortunately, there is a way to trap antihydrogen because it has a small magnetic moment. So a second magnetic trap was engineered around the device which could capture the antihydrogen.
Unfortunately, that trap is pretty weak, so most antihydrogen atoms escape and annihilate. But a few stay. And the idea then is simple. Slowly weaken the magnetic field holding them, and as the trap gets weaker and weaker, anti-atoms start to escape. And if gravity pulls antimatter down, like normal matter, then more atoms should escape through the bottom than through the top.
So what did they find? Does antimatter fall up or down?
They found that antimatter falls down, so it rules out any exotic theories of anti-gravity. They measured the gravitational acceleration as 75% of normal gravity, plus minus 13%, plus minus 16%, which is possibly consistent with normal gravity, but of course the error bars are huge.
And this is also why G-Barr is so important, because their hope is to get the measurement accuracy down to 1%, and ultimately to 1 in 100,000. See, when you're doing a gravity experiment on atoms like this, you want those atoms to be as still as possible before you drop them. In other words, you want them to be as cold as possible. Now, alpha G can get really cold to about 0.5 Kelvin, which is half a degree above absolute zero. But G-Barr wants to bring this way down to less than 10 microkelvin. That is 50,000 times colder. The way they plan on doing this is actually not by making antihydrogen atoms, but by making an antihydrogen ion. 1 antiproton and 2 positrons. The hope is that once an antihydrogen atom has formed, it runs into a second positronium atom and steals another positron. At first, that might seem strange, because now we're back to having a charged particle. And as we learned, you can just drop a charged particle and measure the effects of gravity. But charged particles are actually much easier to trap and cool. And we can use that, because now it can be held in a much stronger electromagnetic trap. And once there, you can inject ultra-cold, like 10 millikelvin beryllium ions that have been laser cooled. The antihydrogen ion then bounces around and collides with these beryllium ions, slowly transferring its kinetic energy to them and thus cooling down. And they won't annihilate, because both particles are positively charged, so they repel each other. Then you keep cooling down the beryllium ions using more advanced techniques, until you hit the microkelvin range. And this is ultimately how they hope to reach a temperature of around 10 microkelvin. Now, with the antihydrogen ion as still as possible, they shoot a laser pulse at it, dislodging one of its positrons and resulting in a neutral antihydrogen atom. And as a result, the electromagnetic trap can no longer hold it, and so it falls. around 20 centimeters. At that temperature and over that distance, you can time the fall precisely enough to measure the gravitational acceleration to about 1%. So all of this, the particle accelerator, making the positronium, and then the hard way of cooling it, all of it is just to watch a single antiatom fall 20 centimeters. Because this process is the only known way to make antihydrogen ions. And using those ions is the only way to get antimatter cold enough to perform an accurate enough experiment. Now, they haven't managed to do this yet. So far, they've only made antihydrogen. But if they can manage, then it would be the most precise measurement of antimatter under gravity. Although this is likely still years away. Now, one thing that makes this research so tricky and also relatively slow is that there is only one antimatter factory in the world. And so the number of places that can study real antimatter is very limited. But that might soon change, all thanks to another experiment at the factory. The base experiment was built to measure the magnetic moment of the antiproton. If CPT symmetry holds, then it should be exactly equal and opposite to that of the proton. But they kept running into a problem.
Accelerator is continuously ramping magnetic fields in the background.
Right.
Even though these fluctuations were tiny, around 20,000 times weaker than the Earth's magnetic field, at the precision base was working at, they hit a wall.
The only concept basically to overcome this problem is to move the particles out of the accelerator.
So they built a penning trap with its own power supply, its own cooling system, and 2 storage holes for antiprotons. So now they could fill those holes with antiprotons, store them, and carry them to wherever they wanted. They just created the world's first portable antimatter trap. So, of course, I asked them a pressing scientific question.
Are you gonna make it look super futuristic? Because it's gotta be the most badass transport container ever made.
I just have this trap here in my office. Maybe I can show it to you.
Oh, yes, please. Oh,
This is one of these penning traps, and they are inside the superconducting magnet. So the heavy part is basically the superconducting magnet, but these are these trap electrodes.
And it works. They have cracked the code of storing the most volatile substance in the universe. Their current record for storing antiprotons is 614 days. That is, they can store antimatter, you know, the stuff that annihilates as soon as it touches matter, for close to 2 years. That is absurd.
This is this antiproton reservoir trap that stores antiprotons for longer than 1 or 2 years.
That's awesome.
But here's what that means. Because if you can store antimatter 4 years in a box, and you can put that box on a truck, then why not ship it?
We can start distributing antiprotons to ambitious experiments all around the planet. And everyone who has a good idea what we could do with these particles will get these particles.
I'm just imagining this map in my head where you have the big antimatter factory, and then it's gonna be sending antimatter all over the world to all the top research institutions.
That's great, right? That's
It's awesome.
Fantastic
It's
vision.
fantastic. Yeah.
Yes.
And they've already started. On the 24th of March, 2026, a crane lifted an 800 kilogram trap out of the antimatter factory and loaded it onto a truck, which then drove on a 10-kilometer loop around CERN. And it was filled with 92 antiprotons. So perhaps Angels and Demons wasn't that far off after all. In the near future, there could be actual boxes of antimatter that, at least in theory, could be stolen. So does that also mean that they were right about that 1/8 of a gram of antimatter? Well, we wanted to find out, so we tested it. I mean, we simulated it.
This is like the most supervillain call I've ever got.
I'm really getting into my villain arc here. Okay, so let's find our poor target, Vatican City. We've got 1/8 of a gram, you know, selected right there, 0.125. Who wants to do a countdown?
3, 2, 1. Let's go!
Let's go!
Oh my god.
Okay, so we've got a few levels of destruction here. We've got the fireball. This is just all instantly vaporized. It's turned into pure plasma, which is insane.
Oh, St. Peter's Basilica.
It's got a temperature of about 100 million degrees Celsius, which is, pretty chill. You can see it released about 2.25 times 10 to the 13 joules, or I guess about 22 trillion joules, which is the equivalent of like 36% of the Hiroshima blast. If we zoom out, this is the area of third-degree burn, so your skin gets molten.
Bro, you're having way too much fun with this. Can I ask this question? Like, do we have an 1/8 of a gram of antimatter available for this? Asking for a friend.
Can you really steal 1/8 of a gram from CERN?
That's a good question.
Do you know how much antimatter you've made in total in this factory?
We make in the order of 10 to the 10 antiprotons per year. Now we can make an estimate. This facility is around since 25 years. So let's say this is 10 to the 11 protons. A gram would mean 10 to the 23. So we are talking here of, well, I'm not very good at math, but it's like
A trillionth of a gram.
That means that to make 1/8 of a gram of antimatter, the factory would have to run for longer than the age of the universe. In fact, if you took all the 10 billion antiprotons they make in a year and annihilated them all at once, you would produce enough energy to heat 1 milliliter of water by about 1 degree Celsius.
I'd love to see Croatia get, just for size and scale.
How much?
You tell me.
All right. 10 grams of antimatter.
Sure, let's do it.
Oh my god.
So while 10 grams of antimatter would destroy an entire city,
Bye-bye hometown.
the amounts of antimatter they're making at CERN are in no way dangerous. Which is also part of the reason we had some fun with this simulation. Because for the far foreseeable future, it's just not realistic to talk about having macroscopic amounts of antimatter.
Yeah, so if people want to play around with this, we'll put a link in the description. Yeah, have fun.
Or if you'd rather get some antimatter yourself without having to rob CERN, then I'll tell you how to get some. Just go to your local supermarket and buy yourself this, some bananas.
That's because a banana contains trace amounts of the radioactive isotope potassium-40. And roughly every 75 minutes, one of these atoms decays and releases a positron. Which means that if you wanted to match the Antimatter Factory's output in terms of antiparticles, you would need about 1 billion bananas.
Now that's a lot of bananas, and I don't recommend eating that many. But the thing is, even if you never eat any bananas, odds are there are some trace amounts of radioactive materials inside of you. And some of those will produce antimatter. One article estimates that the average human makes around 180 positrons per hour. And so there truly is no need to be scared of antimatter, because you have been your own little antimatter factory all along. Hey, just a few final things. The first thing is I want to give a big shout out to Physics Girl, who made an amazing video for the Antimatter Factory years ago. And ever since I watched that video, I've always wanted to go. So it's been a huge inspiration, and I highly recommend you check out that video here. The other thing is, I want to give a quick shout out to all the people at CERN, those who helped us with all the animations, those who've hosted us and taken the time to explain their life work, and everyone else. Thank you so much. And the third and final thank you is, of course, as always, to you. Thank you so much for watching, and I'm excited to see you at the next one. Anti-Casper, Casper, annihilate. All right, that's it.